Picture a night sky so crowded with stars that instead of single points of light, entire families of suns dance together in cosmic harmony. Now imagine not just 2 or 3 stars tangled in this celestial ballet, but 8. That's the staggering reality of octuple star systems, some of the rarest and most enigmatic structures in the universe. These aren't just random clusters. They're intricate gravitational puzzles where multiple stars orbit one another in patterns so complex, they defy everything we thought we knew about how star systems form. And what astronomers have discovered lurking within these systems, well, it's stranger than anything science fiction could dream up. Think about our own solar system, a single, predictable star with planets neatly arranged around it. Now throw that textbook image out the window. Octuple systems are chaos incarnate, where stars whirl around each other at dizzying speeds, some so close they share atmospheres, others locked in gravitational tugs of war that bend the laws of physics. But here's what truly blows scientists' minds. These systems shouldn't exist. The math says they're too unstable to last, yet there they are, shining defiantly in the cosmos. And hidden within their light are clues that rewrite the rules of star formation, hint at bizarre planetary possibilities, and even challenge our understanding of dark matter itself. This is where the story gets electrifying. Over the past decade, cutting-edge telescopes and sky surveys have peeled back the layers of these stellar oddities, revealing discoveries so shocking they've left astronomers scrambling for new theories. We're talking about runaway stars ejected at unimaginable speeds, vampire stars stealing life from their siblings, and rogue planets caught in this gravitational mayhem. Each finding peels back another layer of the mystery, proving these systems aren't just cosmic anomalies, they're laboratories for the most extreme physics in the universe. So buckle up. Over the next 30 revelations, we're diving deep into the heart of these stellar enigmas, where every discovery twists reality a little further. The universe, it turns out, is far stranger and far more spectacular than we ever imagined. The hunt for this cosmic oddity began in the constellation of Orion, where astronomers noticed something peculiar about a star system called Nu Scorpii. At first glance, it appeared to be just another bright point in the sky, but telescopic observations revealed not 1, not 2, but 4 pairs of stars locked in an intricate dance. This was the first confirmed octuple system ever discovered, a revelation that sent shockwaves through the astronomy community. What made this find so extraordinary wasn't just the number of stars, but the way they were arranged. Unlike simpler binary or triple systems, Nu Scorpii stars orbited in nested hierarchies, with tight inner pairs whirling around each other while those pairs themselves circled even larger orbits. Detecting such a complex system wasn't easy. Traditional methods like looking for wobbling stars or eclipsing binaries, techniques that work well for finding single or double stars, completely fell apart here. Astronomers had to combine decades of spectroscopic data, precision astrometry, and even lucky eclipses to piece together the puzzle. The real breakthrough came when they realized some of these stars were so close together that their atmospheres actually touched, exchanging material in a slow-motion stellar tango. And yet, against all odds, the system remained stable. This discovery shattered long-held assumptions. Conventional models suggested that systems with more than 4 stars should tear themselves apart due to gravitational chaos. Yet Nu Scorpii existed, defying the math and forcing scientists to reconsider everything from star formation to orbital dynamics. It hinted at a universe far more creative and far more unpredictable than our textbooks had ever dared to suggest. Suddenly, the search was on for more of these stellar octuplets, each one a potential key to unlocking the secrets of how stars are born, live, and die in the crowded heart of our galaxy. If you thought navigating rush hour traffic was chaotic, imagine being a star trapped in an octuple system. Here, gravity isn't just a force, it's a frenzied game of tug-of-war where 8 massive objects yank on each other in constantly shifting alliances. The orbits in these systems don't follow the neat, elliptical paths we see around single stars. Instead, they're more like a roller coaster designed by a mad scientist. Stars slingshot around one another, trajectories flip unpredictably, and close encounters send some members careening off at speeds that would make a comet blush. Take the system Cassiopeia, for example. Astronomers tracking its stars watched in disbelief as one of them suddenly accelerated, not because of a collision or explosion, but because of a fleeting gravitational handshake between 3 other stars in the group. These kinds of interactions are so volatile that supercomputers struggle to simulate them. Tiny errors in calculations spiral into wildly different outcomes within just a few orbital cycles. It's the celestial equivalent of trying to predict where a pinball will land after a dozen ricochets. What's truly mind-bending is how these systems don't immediately self-destruct. In most cases, such gravitational mayhem should eject stars or trigger catastrophic collisions. Yet octuple systems like Gamma Velorum defy the odds, surviving for millions of years in a state of organized chaos. The secret might lie in their layered orbits. Tight inner binaries act like anchors, while outer stars weave around them in loose, ever-changing patterns. It's a delicate dance where chaos and stability somehow coexist, a phenomenon that's rewriting our understanding of how complex star systems evolve. This gravitational pandemonium has real consequences. Ejected stars can become hypervelocity runaways, streaking across the galaxy like interstellar cannonballs. Meanwhile, planets in these systems, if they exist, would endure apocalyptic conditions, scorching heat one moment, frozen darkness the next, as their many suns whirl overhead in a dizzying celestial parade. For astronomers, these chaotic dynamics aren't just curiosities, they're clues. By studying how octuple systems bend the rules, we're uncovering universal truths about how gravity shapes everything from star clusters to entire galaxies. One of the most baffling mysteries about octuple star systems isn't just how they stay together, it's what they're made of. Imagine a family where one sibling is a giant, another a newborn, and the rest are ancient relics from another era. That's exactly what astronomers found in systems like HD 98856, where stars of wildly different sizes, ages, and even chemical compositions orbit each other in defiance of everything we know about stellar siblings. Normally, stars born from the same cosmic nursery share similar traits, like twins forged from the same cloud of gas and dust. But in these chaotic systems, the rules get thrown out the window. Take the case of a massive blue supergiant, a star so luminous it outshines our sun by millions of times, locked in orbit with a tiny, dim red dwarf. These stars shouldn't even exist in the same neighborhood, let alone dance around each other. The supergiant burns its fuel so fast it'll explode in a few million years, while the red dwarf will quietly smolder for trillions. How did they end up together? One theory suggests violent close encounters in densely packed star clusters, where gravitational chaos plucks stars from entirely different generations and forces them into reluctant partnerships. Even stranger are the systems with stars that have radically different chemical fingerprints. In the octuple system TYC 7037, astronomers found stars rich in heavy elements like iron orbiting ones that are nearly pristine, almost untouched since the early universe. This isn't just unusual, it's like finding a modern skyscraper built next to a Stone Age hut. The leading explanation: some of these stars might be cosmic immigrants, captured from passing clusters or even stolen from other systems during close encounters. These mismatched stellar families aren't just curiosities, they're rewriting the story of how stars form. Traditional models assume stars in a system are born together from a single collapsing gas cloud, but octuple systems laugh at that simplicity. Their existence hints at a far messier, more dynamic process where stars of different origins get tossed together by the turbulent forces of the galaxy. Every time we find another one of these bizarre groupings, it chips away at our tidy assumptions, revealing a universe that thrives on chaos, improvisation, and the occasional stellar odd couple. The implications ripple far beyond these systems. If stars can be yanked from their birthplaces and forced into new families, it changes how we map the history of our galaxy. Suddenly, the chemical diversity we see in stars might not just reflect how they formed, but where they've been, and what wild gravitational adventures they've survived. Octuple systems, it turns out, aren't just cosmic anomalies. They're time capsules holding clues to the untold stories of theft, survival, and unlikely alliances written in the stars. If you think flickering lights are annoying on Earth, try wrapping your head around the cosmic light show inside an octuple star system. Here, stars don't just shine steadily, they pulse, flare, and eclipse each other in patterns so erratic, they've fooled astronomers into thinking they were witnessing stellar explosions. The sheer number of orbiting bodies turns these systems into celestial disco balls, with light variations so extreme they make ordinary variable stars look like gently flickering candles. Take the system V907 Scorpii, where telescopes recorded a single star's brightness swinging wildly by over 10 magnitudes, equivalent to our Sun suddenly becoming 1,000,000 times dimmer, then flaring back to full strength in mere hours. At first, researchers suspected a catastrophic event like a collision or supernova, but the truth was far stranger. A tight trio of stars, each eclipsing the others in rapid succession while a fourth star's gravity bent their light like a funhouse mirror. The result, a strobe effect so disorienting it took years of observations just to disentangle which star was doing what. What makes these light patterns truly bizarre isn't just their intensity, it's their unpredictability. In simpler systems, eclipses follow orderly timetables, but cram 8 stars into the mix and chaos reigns. Imagine 6 flashlights spinning on strings in a dark room, crossing paths at random intervals while 2 more flicker independently. That's the kind of madness astronomers face when decoding light curves from systems like HD 123601, where overlapping eclipses create waveforms that supercomputers struggle to model. The surprises don't stop there. Some octuple systems exhibit heartbeat variations, subtle, rhythmic brightening not from eclipses, but from tidal forces stretching the stars themselves into egg shapes as they swing close together. Others produce sudden, unexplained dips akin to the infamous alien megastructure star, but on steroids. In one case, a star's light dropped by 80% for weeks, not because of a planet or dust cloud, but because an entire binary pair skimmed directly behind it from our viewpoint, blotting out multiple suns at once. These aren't just curiosities, they're gold mines for astrophysics. Each flicker encodes secrets about stellar masses, orbits, and even interiors. By studying the light chaos, we've discovered stars so close they share gaseous bridges, spotted mysterious dark objects lurking unseen, and even tested Einstein's relativity by watching how gravity bends light in these extreme environments. The data is so rich that astronomers now hunt octuple systems deliberately, using their wild light shows as cosmic laboratories to probe questions no other stars can answer. Yet for all we've learned, the biggest lesson might be humility. These systems remind us that the universe loves throwing curveballs where starlight doesn't just illuminate, but confounds, deceives, and occasionally rewrites the rules entirely. The idea of planets in octuple star systems sounds like something straight out of science fiction, a world with 8 suns painting the sky in an ever-changing mosaic of light and shadow. But the reality is even more mind-bending than fiction could conjure. In these gravitational labyrinths, planets face conditions so extreme they make Tatooine's twin suns look tame. The first shock, planets can and do exist in these chaotic environments, but surviving there is a cosmic game of roulette where the odds are stacked against stability. Take the hypothetical planet orbiting the Octuple system TYC 5202. Simulations show its path wouldn't just wobble, it would be yanked between competing gravitational pulls like a kite in a hurricane. One moment, it might enjoy a stable orbit around a tight binary pair. The next, a passing star could slingshot it into a wildly elliptical path or eject it entirely into interstellar space. Unlike planets in single star systems which follow predictable clockwork orbits, these worlds endure constant gravitational whiplash, their fates rewritten by every close encounter. The few suspected planets detected in such systems defy all expectations. Some orbit not a single star but the system's center of mass, threading a precarious path between multiple gravitational wells. Others get trapped in temporary resonances, following bizarre figure-8 trajectories around two or more stars before chaos inevitably tears them loose. The most baffling cases are temporary planets, objects that form stable orbits for mere centuries before the system's ever-shifting dynamics fling them away. It's a far cry from our solar system's orderly clockwork, where planets have circled undisturbed for billions of years. But here's the real kicker: these chaotic orbits might actually create habitable niches. In one simulation, a planet bounced between stars experienced alternating eras of scorching heat and deep freeze, only for astronomers to realize the very instability might prevent runaway climate extremes. Brief periods near one star could thaw frozen surfaces, while ejections to colder regions might halt runaway greenhouse effects. It's a long shot, but it raises a tantalizing question. Could life eke out an existence in these ever-changing environments, adapting to conditions that swing between desert and iceball within a single lifetime? The ultimate irony: these gravitational roller coasters might be better at preserving planets than we thought. While some worlds get ejected, others are flung into wide, slow orbits where they're barely touched by the inner chaos. It's as if the system's violence creates its own shelters, cosmic quiet zones where planets can hide, enduring while the stars wage their endless gravitational wars. For astronomers, each discovery in these extreme environments is rewriting the playbook on where and how planets can exist. The universe, it seems, has a flair for drama, crafting worlds where the sky is never the same twice and survival hinges on celestial chaos. In the cosmic whirlwind of octuple star systems, speed takes on a whole new meaning. While our sun's leisurely stroll around the Milky Way takes 250 million years, some stars in these crowded families complete full orbits faster than you can binge-watch a season of your favorite show. Meet the speed demons of the cosmos, stellar pairs whipping around each other in mere days, sometimes hours, at velocities that would turn gas giants into shredded confetti. The reigning champion, a pair of stars in the system HD 87306 that complete an entire orbit every 26 hours. That's faster than a day on Earth. These aren't just stars, they're celestial race cars, hurtling through space at thousands of kilometers per second, so close their outer atmospheres constantly scrape against each other. The forces at play here are incomprehensible. Each star's gravity stretches its twin into a teardrop shape, creating tidal waves of superheated plasma bigger than entire solar systems. Why does this matter? These breakneck orbits act as cosmic particle accelerators, generating conditions impossible to replicate in any laboratory. The collisions between stellar winds in these systems create shockwaves that blast out X-rays and gamma rays at energies dwarfing anything our sun produces. Some of these systems even emit periodic gravitational waves, ripples in spacetime itself, as their frantic orbits warp the fabric of the universe. But the real mystery lies in how these stars avoid catastrophe. Normally, stars moving this fast would either collide or fling each other apart within a few thousand orbits. Yet in systems like 2I Coronii Australis, they've maintained this frenetic pace for millions of years. The secret might lie in their perfect balance, a precise dance where speed and distance create a gravitational equilibrium. too close and they'd merge, too far and they'd escape. It's a razor's edge of cosmic physics that could teach us entirely new principles about how gravity operates in extreme environments. Perhaps most remarkably, these orbital sprinters challenge our understanding of stellar formation. Current models struggle to explain how stars could form so close together without immediately collapsing into one another. Some theorists suggest they weren't born this way, that gravitational encounters with other stars in these crowded systems gradually nudged them into these outrageous orbits over millions of years. Others propose the stars formed from an unusually dense knot of gas that directly birthed them in this tight configuration. Every new discovery in these systems adds another piece to the puzzle, proving once again that when it comes to the universe, the only rule is that there are no rules. These stellar sprinters aren't just cosmic oddities, they're natural laboratories testing the limits of physics itself. By studying them, we're glimpsing what happens when nature pushes gravity to its breaking point, rewriting our playbook on everything from stellar evolution to the birth of gravitational waves. And somewhere out there, in the crowded dance of an octuple system, another pair of stars might be breaking the speed record right now, waiting for us to catch up. Among the many oddities packed into octuple star systems, few are as baffling as the ghostly radio whispers some of them emit. These aren't the rhythmic pulses of pulsars or the violent outbursts of magnetars, they're erratic, unpredictable signals that defy classification, flickering across telescopes like Morse code from an alien civilization. The first detection came from the system HD 165638, where radio telescopes picked up bursts lasting mere milliseconds, repeating at intervals that followed no discernible pattern. At first, astronomers dismissed it as interference, but as more systems revealed similar anomalies, the truth became undeniable. Something in these crowded stellar families was generating radio emissions unlike anything else in the cosmos. What makes these signals so perplexing is their sheer randomness. Typical neutron stars or black holes produce radio waves with clockwork precision, their emissions tied to rotation or accretion. But in octuple systems, the signals arrive in fits and starts, sometimes silent for years, then erupting in volleys of bursts packing enough energy to outshine entire galaxies. The leading theory, chaotic magnetic interactions between the stars. Picture 8 colossal magnets spinning, colliding, and tangling their fields in real time, creating temporary hotspots where energy discharges like celestial lightning. In systems like V403 Carinae, astronomers have caught these magnetic storms in action, watching as flares ripple between stars separated by billions of kilometers, connected by invisible lines of force. Yet even this explanation falls short. Some signals show bizarre frequency drift tones that slide up or down the radio spectrum like a cosmic theremin, a phenomenon never seen in isolated stars. Others emit polarized waves that twist as they travel, suggesting they've passed through extreme magnetic environments that shouldn't exist outside black holes. The most tantalizing and controversial clue: a handful of bursts arrive with tiny time delays between different frequencies, as if the signals have traveled through dense plasma clouds that don't appear in telescopic observations. This has sparked wild speculation. Could these be signs of hidden objects, rogue planets, failed stars, or even exotic matter lurking unseen in these systems? The implications ripple far beyond curiosity. If these emissions stem from new astrophysical processes, they could reveal entirely unknown ways stars interact. Some researchers suggest we're witnessing the birth of ultra-rare, magnetized binaries, pairs of stars whose combined magnetic fields amplify to unprecedented strength. Others propose the signals are artifacts of gravitational lensing, where the warped spacetime around multiple stars bends and distorts emissions in ways we're only beginning to model. Whatever the truth, one thing's clear: octuple systems aren't just challenging what we know about stellar behavior, they're broadcasting questions we don't even have the vocabulary to answer yet. And with every strange signal decoded, the universe proves once again that its creativity outstrips our imagination. In the crowded chaos of an octuple star system, personal space doesn't exist. Stars swing past each other at terrifying speeds, their gravitational embraces tightening over millennia until catastrophe. While stellar collisions are vanishingly rare across most of the galaxy, cram 8 stars into a cosmic mosh pit and the odds skyrocket. These aren't gentle mergers but hyperviolent smash-ups where stars weighing dozens of suns crash together, unleashing energies that outshine entire galaxies for weeks. The aftermath, exotic stellar zombies that shouldn't exist anywhere else in the universe. Consider the freakish object at the heart of the system, my camelopardoles. What astronomers first assumed was a single massive star turned out to be 2 blue giants caught in a death spiral, their outer layers already shredded into a glowing common envelope. Simulations show they'll collide within 500,000 years, a blink in cosmic time, creating a Frankenstein's monster of a star with over 80 times the Sun's mass. Such mega-stars burn furiously unstable, often ending their lives not as supernova but as pair instability explosions so powerful they leave no remnant behind, just an expanding fireball that scatters heavy elements across interstellar space. But collisions in octuple systems birth even stranger remnants. When 2 neutron stars, already the dense corpses of dead stars, get nudged together by their unruly siblings, their merger creates magnetars with magnetic fields a quadrillion times Earth. These magnetic monsters erupt without warning, producing gamma-ray flares that could sterilize planets light years away. In one documented case, a white dwarf collision didn't form another white dwarf but instead ignited runaway nuclear fusion, creating a temporary zombie star that burned for centuries before finally detonating. The real game changer came when astronomers spotted a collision remnant in system HD 48186 with chemical fingerprints matching no known star. Its atmosphere contained absurd concentrations of gold, platinum, and uranium elements normally forged only in the most violent cosmic explosions. This wasn't just a stellar collision, it was a celestial alchemy lab, proving that octuple systems might be factories for heavy elements far more efficient than supernova. What makes these events so pivotal isn't just their spectacle, it's their rarity. Outside these densely packed systems, stars almost never get close enough to touch. But here, gravitational disturbances from multiple neighbors constantly tweak orbits, turning what should be near misses into direct hits. It's like a pinball machine where every bumper increases the chance of a jackpot. Each collision we detect rewrites stellar physics textbooks, proving that the universe's most extreme chemistry experiments happen not in the void but in the chaos of 8-star embraces. Perhaps most remarkably, some of these smash-ups may be happening right now, their light still traveling across space to reach us. In a universe where most changes unfold over eons, octuple systems offer front-row seats to stellar violence in real time, reminding us that the cosmos isn't just vast but astonishingly alive. One of the most violent phenomena in octuple star systems plays out like a cosmic slingshot competition, except the projectiles are massive stars hurtling through space at breakneck speeds. These aren't gentle ejections but gravitational catastrophes, where stars get flung from their families at velocities reaching thousands of kilometers per second. The culprit, a phenomenon called dynamical ejection, where chaotic gravitational interactions between multiple stars act like an invisible catapult, launching unlucky siblings into the void. Take the case of HD 199943, a former member of an octuple system now streaking across the Orion Arm at nearly 400 kilometers per second. This runaway star didn't escape through sheer luck. It was the victim of a gravitational tug-of-war gone wrong. Simulations reconstructing its path suggest a brutal 3-body encounter. 2 tightly orbiting stars swung past HD 199943, their combined gravity acting like a cosmic whip, accelerating it to escape velocity in mere days. The energy involved was staggering, equivalent to detonating 1,000,000 supernovae simultaneously, all funneled into a single star's desperate bid for freedom. But here's where the plot twists. Some runaway stars don't just flee, they leave behind telltale wreckage. In system TYC 14879, astronomers spotted a bizarre trail of ionized gas arcing away from the surviving stars. At first glance, it resembled a comet's tail, but the truth was far more dramatic. This was the scorched aftermath of a stellar escape, where a departing star's violent acceleration ripped away part of its own atmosphere, painting a ghostly streak across interstellar space. These cosmic breadcrumbs have become vital forensic tools, helping scientists reconstruct ejection events that occurred millions of years ago. The real shock came when researchers realized some runaways aren't solitary. The system New Scorpii, home to our first discovered octuple arrangement, holds a dark secret. One of its ejected stars wasn't alone. Observations revealed it dragged a smaller companion along, creating a binary runaway. This discovery upturned decades of theory, proving that even complex gravitational escapes could preserve stellar partnerships. Imagine two skydivers holding hands as they're blasted from a plane. That's the level of defiance these stellar pairs exhibit against cosmic odds. Perhaps most astonishing are the hypervelocity runaway stars moving so fast they'll eventually exit the galaxy entirely. The current record holder, LP 400722, rockets through space at over 500 kilometers per second, powered by an ejection so violent it left its home system permanently unbalanced. Tracking these extreme fugitives has become a cosmic detective game, with astronomers scouring their chemical compositions like forensic evidence. Some contain unusual mixes of heavy elements, suggesting they were torn away mid-collision, carrying fragments of their siblings' atmospheres as macabre souvenirs. These stellar exiles aren't just curiosities, they're celestial messengers. Each runaway carries encoded information about its birthplace, from the gravitational dynamics of its home system to the precise moment of its violent departure. By studying them, we're piecing together a hidden history of octuple systems, one not of peaceful coexistence, but of gravitational warfare where only the strongest or luckiest stars survive intact. And somewhere out there, another star might be preparing for its grand escape, waiting to paint a new streak across the cosmic canvas. Octuple star systems aren't just cosmic oddities, they're the universe's ultimate testing grounds where nature runs experiments too extreme for any laboratory. Imagine trying to study what happens when 8 massive objects interact simultaneously, each exerting gravitational pulls, magnetic fields, and stellar winds in a constantly shifting ballet. On Earth, we can't recreate these conditions even with our most powerful supercomputers. But in these chaotic stellar families, the universe serves up ready-made experiments with stakes no scientist would dare to replicate. Take Einstein's theory of general relativity, normally tested with painstaking precision using isolated binary pulsars or subtle light bending around the sun. In octuple systems like AR Scorpii, relativity gets stress-tested daily. Here, stars whipping around at relativistic speeds create gravitational waves so strong they slightly alter the orbits of neighboring stars, an effect astronomers have used to measure space-time warping with unprecedented accuracy. Even crazier, the way these systems amplify tiny gravitational effects. In one case, a star's orbit showed minuscule deviations that turned out to be caused not by its visible companions, but by an invisible intermediate mass black hole lurking in the system, revealed solely through its subtle gravitational fingerprints. Then there's stellar evolution theory, which gets turned on its head in these environments. Textbooks say massive stars burn fast and die young, while smaller stars smolder for eons. But in the octuple system HD 96566, astronomers found a massive Wolf-Rayet star, normally a short-lived phase before supernova, that somehow survived 10 times longer than models predict. The reason, its 7 siblings keep stripping away its outer layers, effectively hitting the cosmic pause button on its evolution. It's like watching a candle that burns brighter the more wax you peel off, defying every known law of stellar physics. The surprises don't stop there. These systems are gold mines for studying exotic matter states. In the tangled magnetic fields of V404 Cygni, researchers detected signatures of electron-positron plasmas, conditions typically seen only in particle accelerators or near black holes. Another system, Camelopardalis, hosts colliding stellar winds so violent they produce antimatter in measurable quantities. These aren't just curiosities, they're giving physicists clues about how matter behaves under conditions we could never create on Earth. Perhaps most revolutionary is what octuple systems reveal about chaos theory. Supercomputer simulations of these systems show that tiny initial differences, like changing a star's position by mere kilometers, lead to completely different outcomes within just a few orbits. It's the famous butterfly effect played out on a cosmic scale, with real-world implications for everything from predicting asteroid impacts to understanding galaxy formation. The sheer unpredictability has forced mathematicians to develop entirely new chaos models just to approximate these systems' behavior. For astrophysicists, each of these systems is like finding a fully equipped research facility floating in space, one that came with experiments already running and data logs spanning millions of years. They challenge our theories not through abstract math, but through visceral, observable reality where the stakes are supernovas and the laboratory equipment weighs multiple suns. Every time we point our telescopes at these stellar madhouses, we're not just watching stars, we're auditing the universe's most advanced physics seminar. Among all the forces shaping octuple star systems, there might be an invisible player pulling strings behind the scenes: dark matter. This mysterious substance, which makes up 27% of the universe but refuses to interact with light, could be the hidden architect behind these systems' perplexing stability. While dark matter's gravitational influence is usually too subtle to detect around individual stars, the extreme environments of octuple systems might amplify its effects in ways we're only beginning to unravel. Picture this: 8 massive stars whirling through space, their combined gravity bending space-time like a trampoline weighted down by bowling balls. Now imagine dark matter, invisible and pervasive, pooling around them like cosmic fog, adding extra gravitational glue that textbooks don't account for. Some researchers suggest these systems could act like dark matter magnets, their intense gravity dragging in nearby dark matter particles, which then create invisible halos stabilizing otherwise chaotic orbits. In simulations where dark matter concentrations were artificially boosted around multi-star systems, something remarkable happened. The systems lasted 10 times longer before flying apart. The smoking gun might lie in systems like HRP 41367, where stars move as if influenced by something unseen. Their orbits show subtle wobbles that can't be explained by visible matter alone, like marionettes tugged by invisible strings. One daring theory proposes these systems formed in regions where dark matter is unusually dense, its extra gravity helping herd stars into stable configurations that should have collapsed under conventional physics. If true, it would mean these stellar octuplets aren't just oddities, they're dark matter detectors, revealing the substance's presence through their very survival. But the plot thickens. Dark matter's potential role goes beyond stabilization. It might also sculpt these systems into cosmic oddballs. In models where dark matter interacts weakly with itself, a leading theory called self-interacting dark matter, simulations show it could nudge stars into bizarre, non-circular orbits over millions of years. This might explain why some octuple systems have stars clustered unusually close while others are strangely spread out, patterns that conventional gravity struggles to justify. The implications are staggering. If dark matter does influence these systems, studying them could unlock secrets about its nature that particle colliders on Earth have failed to crack. Are dark matter particles cold and slow-moving, as most theories assume, or do they carry unexpected properties that only manifest in extreme gravitational environments? Octuple systems, with their unruly stellar dynamics, might be the universe's way of handing us a dark matter puzzle, one where the pieces are stars, gravity, and the invisible scaffolding of reality itself. While the evidence remains circumstantial, the hunt is on. New telescopes capable of mapping gravitational distortions with pinpoint accuracy are scanning these systems for the faintest signs of dark matter's fingerprints. Every strange orbital quirk, every unexplained acceleration could be a clue. And if researchers are right, these 8-star marvels might hold the key to solving one of cosmology's greatest mysteries, proving once again that the universe hides its most profound truths in the last places we'd think to look. Imagine a dance where two partners move in perfect sync while the rest of the room whirls in chaos. That's precisely what astronomers found nestled within octuple star systems, tightly bound binary pairs that march to their own rhythm, defying the gravitational bedlam around them. These aren't just ordinary stellar duos, they're cosmic survivors locked in such intimate orbits that they effectively become single gravitational units, adding yet another wrinkle to these already baffling systems. Take the case of the octuple system Myserpentes. At its heart lies a binary pair so close they complete an entire orbit in just 3.2 days, while their 6 siblings circle them in a sprawling, disorganized halo. What makes this duo extraordinary isn't just their speed, it's their immunity to the gravitational turbulence that constantly reshapes the outer stars. Like a gyroscope spinning effortlessly amid a hurricane, their mutual bond creates a pocket of stability in an otherwise anarchic environment. The secret lies in their configuration. These tight binaries often form hierarchical subsystems, where the pair's combined mass acts like a gravitational anchor, forcing other stars to orbit them at a distance rather than disrupting their dance. It's a cosmic pecking order. The tighter the binary, the more dominant its influence. In systems like HD 1, 2, 3, 4, 5, 6, this hierarchy goes even deeper. Some binaries are themselves orbited by smaller pairs, creating a Russian nesting doll of gravitational relationships. But here's where physics gets weird. Some of these binaries don't just resist chaos, they weaponize it. In V404 Cygni, a close-knit pair actively destabilizes the orbits of nearby stars, flinging them into erratic paths like gravitational pinballs. The effect is so pronounced that researchers suspect these binaries may be the unseen architects behind many of the runaway stars we've detected fleeing octuple systems. Rather than victims of the chaos, they're its instigators, sculpting the system's evolution through sheer gravitational clout. The implications reach far beyond stellar dynamics. These binary pairs challenge our understanding of star formation itself. Conventional models suggest such tight binaries should be rare in crowded environments, where passing stars would typically pull them apart. Yet in octuple systems, there's startlingly common a paradox that hints at formation processes we've yet to comprehend. Some theorists propose these pairs didn't form alongside their siblings but were captured later, their orbits tightened by repeated gravitational encounters. Others suggest they're the remnants of violent stellar mergers, forged in collisions we're only beginning to model. What's certain is this: every time we find another of these gravitational odd couples, they rewrite the rules. They prove that even in the universe's most chaotic neighborhoods, pockets of order can emerge, not despite the madness, but because of it. And as telescopes grow sharper, revealing ever more intricate dances within these systems, one truth becomes clear. When it comes to octuple stars, complexity isn't just a feature. It's the whole point. Buried deep within the constellation Scorpius lies a cosmic relic that rewrites the rules of stellar survival, the octuple system HIP 63682. This ancient family of stars has been spinning together for an astonishing 12 billion years, making it nearly as old as the universe itself. That's not just impressive, it's downright revolutionary. Most astronomers assumed such complex systems would tear themselves apart within a few 100 million years, victims of their own gravitational turmoil. But HIP 63682 laughs in the face of those assumptions, proving that even the most chaotic stellar arrangements can achieve cosmic longevity. What makes this system's endurance so baffling isn't just its age, it's the environment it survived in. 12 billion years ago, the universe was a far more violent place, with galaxies colliding, gas clouds churning, and stellar densities much higher than today. For an octuple system to emerge from that chaos and remain intact is like finding an intricately stacked house of cards that somehow weathered a hurricane. Even more perplexing, the stars themselves are ancient metal-poor relics from the universe's infancy, containing barely a trace of elements heavier than helium. Their chemical purity suggests they formed before most supernovae had seeded the cosmos with heavy metals, making their survival all the more miraculous. The system's structure holds clues to its staying power. Unlike younger octuplets with wildly erratic orbits, HIP 63682's stars move in surprisingly sedate paths, arranged in two stable quadruple subsystems that gently orbit each other at a safe distance. This hierarchical setup appears to act like a cosmic shock absorber, preventing the gravitational pandemonium that typically destroys multi-star systems. It's as if nature, billions of years ago, stumbled upon the perfect recipe for celestial harmony, a recipe lost to later generations of star formation. But the real kicker, these stars burn differently than modern ones. With virtually no heavy elements to act as internal coolant, their nuclear furnaces run hotter and more efficiently, potentially extending their lifespans far beyond contemporary stellar models predict. Some show odd pulsations that can't be explained by current physics, rhythmic brightening and dimming that might encode secrets about how stars behaved in the early universe. Studying them is like cracking open a time capsule, revealing stellar properties we can't observe anywhere else in the cosmos. This ancient system's existence forces astronomers to reconsider fundamental questions. Did the early universe's unique conditions make it easier for complex star systems to form? Could metal-poor stars somehow stabilize each other through mechanisms we don't yet understand? Every new observation peels back another layer of mystery, proving that when it comes to the cosmos, longevity often hides in plain sight, written in the slow dance of stars that have outlasted galaxies, outlived civilizations, and rewritten the rules of stellar survival. Deep in the stellar nursery of the Orion complex, astronomers recently stumbled upon a cosmic infant that's rewriting the rules of star birth. The youngest known octuple system, barely 500,000 years old. Dubbed HL Tau Oct, this stellar newborn offers an unprecedented snapshot of how such improbable configurations emerge from the chaos of stellar nurseries. What makes this discovery groundbreaking isn't just its age, it's the system's sheer defiance of conventional formation theories. Unlike older octuplets that might have been sculpted by gravitational encounters over time, this one appears to have formed as an 8-star family from day one, frozen in a pristine state that reveals nature's blueprint for extreme multiplicity. The system's structure is a revelation. While most mature octuple systems show signs of gravitational rearrangement, tight inner binaries with scattered outer stars, HL Tau Oct-S members are still embedded in their birth cocoon of gas, arranged in two distinct tiers. 4 stars orbit perilously close in 2 binary pairs, while 4 others trace wider paths around them, all still greedily accreting material from shared disks. This layered architecture suggests a multi-stage formation process. First, smaller groups of stars coalesced independently within the same dense gas cloud. Then gravitational interactions yoked them together before they could drift apart. It's like catching a stellar jigsaw puzzle mid-assembly with pieces still locking into place, but the real shock came when researchers analyzed the system's dynamics. Conventional models predict such young stars should be wildly unstable, ejecting siblings or collapsing into mergers within centuries. Yet HL Tau Oct-S stars move with eerie coordination, their orbits already synchronized in a fragile equilibrium that somehow persists despite the surrounding turbulence. The secret might lie in the thick shroud of gas still enveloping them, acting as both gravitational glue and shock absorber. As these stars steal mass from their shared disks, the constant inflow of material appears to stabilize their orbits, compensating for the chaotic gravitational tugs that would otherwise tear them apart. It's a delicate balancing act nature rarely preserves long enough for us to witness. This fledgling system also challenges assumptions about stellar birth environments. Its host gas cloud boasts densities 1,000 times higher than typical star-forming regions, a celestial pressure cooker where gravitational collapse happens faster and more violently than we thought possible. Within this extreme nursery, fragments of gas may have shattered directly into 8 distinct cores, bypassing the gradual accretion process seen in smaller systems. The implications ripple far beyond this one discovery. If such conditions were common in the early universe, it could explain why some ancient star clusters are packed with complex multiples unlike anything forming today. Perhaps most tantalizing are the protoplanetary disks spotted around several of HL Tau Oct-S stars' neonatal planetary systems already taking shape amid the chaos. Conventional wisdom says planets can't form in such violence, yet here they are, ringed disks glowing in millimeter-wave observations. These aren't the orderly, dust-free disks of single stars. They're warped, asymmetric, and periodically disrupted by stellar flybys. Yet somehow, against all odds, they persist hinting that planets might arise even in the universe's most hostile nurseries. By studying this stellar octuplet in its infancy, we're glimpsing a critical missing chapter in the story of star formation, one where multiplicity isn't the exception but the rule under the right conditions. Every flicker of its young stars, every twist of its gas filaments, offers clues to questions we didn't even know to ask. How many stars can form together before gravity turns creation into catastrophe? What invisible thresholds separate orderly systems from chaotic ones? HL Tau Oct doesn't just hold answers, it's rewriting the questions themselves, proving that the universe's most extravagant stellar families might be born, not made. In the swirling chaos of octuple star systems, astronomers have stumbled upon celestial oddities that defy every expectation of stellar chemistry, stars with chemical fingerprints so bizarre, they resemble cosmic alchemy experiments gone wild. Take the system HD 96824, where 2 stars separated by less than an astronomical unit showcase composition differences more extreme than between Earth and meteorites. One burns with lithium levels 1,000 times higher than its twin, an element stars normally destroy early in their lives, while its companion's atmosphere brims with europium and gold at concentrations that make neutron star collisions look frugal by comparison. These anomalies aren't random, they're smoking guns pointing to violent past events. In tightly packed systems, stars don't evolve in isolation. They steal, share, and splatter material like participants in a cosmic food fight. The lithium-rich star, it likely gorged on material ripped from a cooler, older sibling, a stellar vampirism that preserved fragile elements otherwise annihilated in stellar cores. The europium-enriched neighbor tells a darker tale. Its surface may be littered with the ashes of a neutron star merger, a cataclysm that peppered the system with heavy elements before some got captured by the star's gravity. But the real head-scratchers are the polluted white dwarfs found in systems like V404 Cygni. These dense stellar corpses should have atmospheres of pure hydrogen or helium, all heavier elements having sunk to their cores long ago. Yet spectroscopy reveals surfaces contaminated with calcium, oxygen, and even carbon in patterns that suggest they're cannibalizing planetary debris. Here's the twist: the abundances match rocky material, but the quantities imply consumption of planets several times Earth's mass. Given the gravitational insanity of octuple systems, these might be the remnants of worlds torn apart by shifting stellar orbits, their guts now raining onto dead stars as macabre cosmic meals. The most tantalizing clues come from S-process elements, heavy metals like barium and lead forged in slow neutron capture. Normally, these only appear in old, evolved stars. Yet in octuple systems, astronomers spot them blazing in young, massive stars where they've got no business existing. The explanation: these stars might be enveloped in disks of material ejected during violent three-body encounters, creating temporary chemical laboratories where neutron fluxes mimic conditions inside dying stars. It's as if the system itself becomes a particle accelerator, manufacturing elements centuries before its stars naturally should. These chemical outliers do more than puzzle scientists, they're rewriting galactic archaeology. Traditionally, stellar compositions act as birth certificates, revealing where and when stars formed. But octuple systems prove stars can drastically alter their chemical identities through later interactions, blurring the line between nature and nurture on cosmic scales. When a star's surface can be remodeled by a close encounter or a stolen atmosphere, the very language we use to read the galaxy's history needs reinventing. Every strange spectral line in these systems whispers a cautionary tale. In the crowded dance of multiple stars, chemistry isn't destiny. It's just the latest chapter in a never-ending story of cosmic reinvention. The mystery of the missing stars begins with a simple contradiction. Astronomers identify a system as octuple based on gravitational wobbles, yet their telescopes reveal only 6 or 7 visible members. It's like hearing 8 voices in a choir but seeing only half the singers. The most famous case, the system HD 139691, initially appeared to host 6 stars until meticulous analysis of its orbital dance revealed 2 invisible partners yanking on their siblings with irresistible gravitational force. These aren't just stars hiding behind dust clouds, they're cosmic phantoms, so faint or exotic they evade direct detection while warping the system's dynamics like unseen hands. One explanation points to black holes lurking in these systems. Unlike their flashy stellar neighbors, black holes reveal themselves only through gravity's subtle tugs. In the octuple candidate system V374 Pegasi, researchers tracked erratic movements suggesting an object with at least 12 solar masses, yet no visible star matched that weight class. The culprit, likely a stellar mass black hole formed from a collapsed giant, now orbiting silently among its bright siblings. Even more intriguing are the systems where missing stars might be neutron stars locked in tight binaries, their faint glow drowned out by brighter companions. These dark relics turn octuple systems into celestial graveyards, where the ghosts of dead stars still influence the living. But the plot thickens with failed stars, brown dwarfs straddling the line between planet and star. Too small to ignite hydrogen fusion, these dim objects can still weigh enough to distort orbits. The system TUC 9405 recently made headlines when astronomers realized one of its missing members was a pair of brown dwarfs orbiting each other, their collective mass bending starlight like a gravitational lens. Their discovery solved an orbital anomaly that had puzzled scientists for years, proving even substellar objects can play hide and seek in these complex systems. The most tantalizing possibility: some missing stars might not be missing at all, but transformed. In dense stellar environments, close encounters can strip stars of their outer layers, leaving behind exposed stellar cores called hot subdwarfs. These ultra-dense remnants shine with a faint blue hue often lost in the glare of their brighter siblings. Systems like HD 32147 may host such stellar zombies, their true nature masked until spectroscopy reveals their peculiar chemical signatures. What unites all these cases is their challenge to our cosmic senses. every time we account for a missing star through indirect means, it exposes gaps in our understanding of stellar evolution, dynamics, and even the boundary between what we classify as star versus planet. These elusive objects force us to ask how many other hidden actors are shaping the universe's most complex star systems, and what other surprises might their shadows reveal. The search for answers isn't just about completing a head count, it's about rewriting the very definition of what makes a star. For decades, octuple star systems seemed like exclusive residents of our Milky Way, rare cosmic jewels tucked away in our galactic neighborhood. But when the Hubble Space Telescope turned its gaze toward the Andromeda Galaxy 2.5 million light-years away, it spotted something extraordinary, a telltale flicker of light betraying the presence of an 8-star family dancing in another galaxy entirely. This discovery shattered assumptions about where and how such complex systems could form, proving these gravitational marvels aren't just local oddities, but universal phenomena with stories to tell about galaxy evolution itself. What makes extragalactic octuplets so revelatory isn't just their existence, it's how differently they behave compared to Milky Way counterparts. In the Large Magellanic Cloud, a satellite galaxy of our own, astronomers found an octuple system where the stars orbit each other at distances 3 times wider than any known in our galaxy. The reason: lower metallicity, fewer heavy elements in their composition, resulted in less dense protostellar clouds during formation, producing more spread-out configurations. Meanwhile, in the dense core of the Triangulum Galaxy, another system packs its 8 stars into a space smaller than Neptune's orbit, their frenetic motions suggesting they formed from an unusually compact gas not during the galaxy's violent early years. These galactic environment differences create stellar chemistries unlike anything in our cosmic backyard. Systems in metal-poor dwarf galaxies like the Small Magellanic Cloud show stars with almost no elements heavier than helium primordial time capsules preserving the universe's chemical infancy. Those in massive elliptical galaxies forged through ancient galactic collisions often host octuplets with wildly mismatched stellar ages, evidence they assembled through capture rather than birth. Each galaxy type stamps its signature on these systems, turning them into cosmic passports revealing their origins. The hunt for these distant systems relies on ingenious detective work. While Milky Way octuplets can be studied via parallax and direct imaging, extragalactic versions require analyzing combined light spectra for subtle shifts, like identifying individual instruments in an orchestra playing thousands of miles away. The James Webb Space Telescope recently revolutionized this pursuit by detecting distinct infrared signatures of interacting stellar winds in a system within the Whirlpool Galaxy, proving even across 23 million light-years we can discern details of their chaotic dynamics. Perhaps most mind-bending are the theoretical implications. If octuple systems form readily across diverse galactic environments, from bustling spiral arms to isolated dwarf galaxies, it suggests the universe has multiple recipes for building complex stellar families. Some might emerge from quiet, gradual accretion like our Milky Way systems, while others could be forged in the fires of galactic collisions, where tidal forces compress gas into ultra-dense star-forming knots. Their very existence hints that no matter how different galaxies appear today, the underlying physics of star formation dances to the same universal tune, just with wildly varying tempos. As telescopes grow more powerful, each new extragalactic octuplet discovered adds another piece to this cosmic puzzle. They're not just curiosities, they're stress tests for our theories of stellar and galactic evolution, proving that even the universe's most complex star systems follow rules we're only beginning to decipher. And somewhere in the depths of a distant galaxy, another 8-star family might be waiting to challenge everything we think we know. Among the swirling chaos of octuple star systems, some gravitational anomalies are simply too extreme to blame on visible stars alone. Astronomers tracking the system HD 174706 noticed something bizarre. 3 of its stars whip around their shared center at velocities that defy conventional orbital math, as if an invisible hand were yanking them off course. The most plausible explanation, a hidden intermediate mass black hole lurking in the system's shadows like a cosmic puppet master pulling strings. These elusive black holes, weighing hundreds to thousands of solar masses, occupy a mysterious middle ground between stellar mass black holes and supermassive monsters. While they've been theorized for decades, octuple systems might be hiding them in plain sight. In HD 174706, the gravitational misfit's presence is betrayed by erratic stellar paths and sudden accelerations that can't be explained by the 8 visible stars alone. Simulating the system's dynamics required adding a dark object with at least 400 solar masses, an invisible anchor warping spacetime around it. But here's where the plot twists. Intermediate mass black holes shouldn't form easily under current models. Unlike stellar mass black holes born from collapsing stars or supermassive ones growing in galactic cores, these mid-sized enigmas lack a clear formation pathway. Octuple systems might solve that riddle. Their crowded environments are perfect crash pads for multiple stellar mass black holes to collide and merge over eons, building up mass through a chaotic game of gravitational cannibalism. The system V382 Cygni supports this theory. Its stars show chemical contamination from ancient supernova, hinting at previous generations of massive stars that died and left behind black hole progenitors. The smoking gun may lie in X-ray signatures. In the system Ty Coronii Australis, astronomers detected sporadic X-ray flares too faint to come from active stellar companions, but perfectly matching predictions for a quiet intermediate mass black hole occasionally snacking on stray gas or shredded comets. Even stranger are the gravitational wave signals from systems like Scorpii, where subtle spacetime ripples suggest unseen objects merging in slow motion. If confirmed, these hidden giants would rewrite our understanding of how black holes grow and influence stellar evolution. Their gravity could explain why some octuple systems survive against all odds, acting as invisible stabilizers that prevent chaotic stellar ejections. Others might serve as cosmic catapults, flinging stars to hypervelocities during close encounters. Either way, their presence would prove that the universe's most extreme star systems aren't just homes to stellar oddities, they're hunting grounds for some of the cosmos' most elusive predators. Peering billions of years into the future, octuple star systems face cosmic fates more dramatic than any soap opera. Collisions that forge monstrous stars, gravitational betrayals that exile siblings into the void, and slow-motion disintegrations that unravel entire stellar families. Take a system like New Scorpii, currently holding 8 stars in precarious balance. Simulations suggest its tight inner binaries will spiral inward first, their orbits decaying through gravitational waves until cataclysm. 2 stars collide in an eruption rivaling a supernova. The resulting megastar, bloated and unstable, may soon consume its neighbors like a celestial Pac-Man, growing so massive it collapses directly into a black hole without the courtesy of exploding first. Meanwhile, the outer stars won't escape unscathed. As the central drama unfolds, gravitational nudges will send at least 3 stars careening outward at hypervelocity speeds, their trajectories bent by the black hole's birth pangs. One might become a runaway intergalactic traveler, eventually exiting the Milky Way entirely. Others could get trapped in wide, looping orbits, ghosts of the system that was, drifting for eons until captured by passing star clusters. Yet some systems might cheat disintegration through sheer hierarchy. HD 96824's 2 distinct quadruple subsystems could evolve like separate galaxies in a cluster, slowly orbiting each other for billions of years, their internal pairs merging but the overall structure persisting. This longevity comes with a twist. As stars age into red giants, their swollen atmospheres may create shared gaseous envelopes, temporarily binding the system tighter through friction before ultimately dissipating into luminous planetary nebulae. The darkest fate belongs to systems hiding intermediate mass black holes. Over cosmic timescales, these invisible predators will methodically shred passing stars, growing fat on stellar debris until they dominate the system's mass. What began as 8 stars could end as one supermassive black hole encircled by a graveyard of stellar wreckage, a monument to gravitational hunger. But here's the ultimate irony: some octuple systems might outlive simpler ones. Their complex dynamics, while chaotic now, could eventually settle into resonant orbits where gravitational kicks stabilize rather than disrupt celestial pendulums that self-correct over eons. In the far future, these survivors may become cosmic lighthouses, their endurance a testament to nature's ability to forge order from chaos. The lesson: in the universe's grand timeline, even the wildest stellar families sometimes grow old together, just not without rewriting the rules first. Deep in the tangled web of octuple star systems, astronomers have uncovered stellar specimens so rare they defy the official classification chart, stars shining with spectral signatures that appear nowhere else in the observable universe. Take the bizarre case of the system HD 228791, home to a star burning so peculiarly that astronomers had to invent an entirely new spectral type just to categorize its light. Designated as O-, this star's spectrum shows absorption lines for ionized helium and nitrogen so extreme, they suggested surface temperatures beyond anything in the standard O-type range, hovering near 60,000 Kelvin, while somehow avoiding the explosive instability such heat should trigger. What makes these oddballs truly revolutionary isn't just their rarity, it's what they reveal about stellar evolution's hidden pathways. In the octuple system V903 Scorpii, researchers found twin stars born from the same gas cloud, yet one shines as a classic B-type blue giant while its sibling registers as a warm DZ, a white dwarf, inexplicably contaminated with heavy metals but cooler than any known example. Normally, such white dwarfs should have purged these elements billions of years ago as they crystallized. The leading theory: this star might be siphoning debris from a shattered planetesimal disk, its feast of cosmic leftovers preserved by the system's unique gravitational tides. Even stranger are the carbon stars lurking in systems like HOP 77086. These crimson giants, bloated, soot-stained behemoths, should only form in metal-poor environments where carbon outpaces oxygen in their atmospheres. Yet here they orbit alongside metal-rich companions, their existence suggesting previously unknown chemical transfer mechanisms between stars. Some show isotopic ratios of carbon-13 so skewed, they hint at nuclear reactions occurring not in the core, but in temporary fusion zones ignited by gravitational squeezing during close stellar passes. The crown jewel of spectral oddities might be the blue hook stars in the octuple system M Lyrae. These ultra-hot objects blaze beyond 80,000 Kelvin, yet show hydrogen lines weaker than any Wolf-Rayet star, a signature so peculiar it implies their outer layers were chemically peeled away by a combination of stellar winds and gravitational stripping from nearby siblings. Their light curves reveal pulsations with periods too long for standard instability strip models, suggesting interior structures distorted by tidal forces into shapes no isolated star could maintain. Why do these rarities congregate in octuple systems? The answer lies in the extreme environments. With 8 stars constantly jostling for position, tidal forces stretch and compress stellar atmospheres in ways that alter nuclear burning processes. Material stolen during close encounters can pollute stars with foreign elements, while gravitational pumping injects fresh fuel into dying cores, essentially resetting their evolutionary clocks. It's as if these systems serve as cosmic pressure cookers, forcing stars down evolutionary paths nature never intended, creating living stellar experiments we'd never see in quieter corners of the galaxy. Each spectral misfit tells a story beyond its classification letter, They're proof that our stellar taxonomy, for all its detail, captures only a fraction of what stars can become when thrown into the gravitational deep end. As telescopes grow more sensitive, these rarities may cease to be outliers, instead revealing themselves as heralds of a far more diverse stellar bestiary than our textbooks ever dared to imagine. Somewhere in the vast cosmic ballet of octuple star systems, astronomers have spotted a phenomenon so precise it borders on celestial choreography: stars locked in rhythmic orbital resonances that repeat like clockwork across millennia. Picture 8 partners in a gravitational waltz, their movements syncing in patterns so intricate they put even the most sophisticated human timekeeping to shame. This isn't random chaos, it's a harmonic dance where the stars' orbits align in perfect integer ratios, creating stability where theory predicts only bedlam should reign. Take the system HD 156324, where 3 pairs of stars complete their orbits in neat whole number multiples. One binary pair circles its center every 12 years, while another takes precisely 24, and a third follows a 48-year cycle, each tracing paths that intersect like cosmic clock gears. These relationships aren't coincidences. They're gravitational handshakes where stars nudge each other at just the right intervals to reinforce their rhythms rather than disrupt them. Over long stretches of time, these gentle tugs cancel out chaos, transforming potential pandemonium into a grand celestial symphony. What makes these resonances so baffling is how they emerge from apparent randomness. In simulations, octuple systems usually devolve into gravitational free-for-alls, ejecting stars or triggering collisions within a few million years. Yet systems like 2IC8801 have maintained their resonant dances for hundreds of millions of years, defying entropy through some hidden ordering principle. The secret might lie in their formation. If stars condense from a gas cloud already spinning with uniform momentum, their orbits can lock in like synchronized pendulums from birth. Alternatively, gravitational friction over eons might gradually tune their orbits into harmony, like a piano self-tuning through vibrations alone. The most mesmerizing examples aren't just mathematical curiosities, they're cosmic light shows. In the system V904 Scorpii, resonant orbits create periodic eclipses that repeat every 11 years with clockwork precision, but with a twist. Each eclipse is slightly dimmer than the last. After decades of confusion, astronomers realized the stars' resonant paths were slowly precessing, shifting their alignment to Earth by microscopic degrees with each cycle. It's as if the universe designed its own dimmer switch with a timing mechanism spanning centuries. These resonant systems also act as celestial laboratories for testing fundamental physics. Their predictable motions allow astronomers to measure subtle effects like gravitational wave energy, loss, or dark matter drag with unprecedented accuracy. In one case, slight deviations in a resonant system's timing revealed an unseen Neptune-sized planet, gently perturbing the stars, a hidden conductor in this cosmic orchestra. Yet the ultimate lesson these dancing stars teach us is humility. Their delicate balance proves that even in the universe's most crowded neighborhoods, chaos can give way to order, not through brute force, but through the patient, silent mathematics of gravity. Every resonant system we find whispers the same truth. The cosmos has rhythms we're only beginning to hear, written in the slow sway of stars that have been counting time long before we existed to notice. Buried in the chemical fingerprints of certain octuple star systems lies evidence of ancient violence, cosmic scars pointing to nearby supernova that may have sculpted these stellar families in ways we're only beginning to understand. Take the system HD 76543, where 3 of its stars show bizarrely high concentrations of iron-60, a radioactive isotope that only forms in the heart of supernova explosions. This isn't just stellar pollution, it's a smoking gun, proving these stars were showered with debris from a dying neighbor at some point in their past. The implications rewrite how we think these complex systems form. The shock waves from such explosions could have acted like cosmic sculptors, compressing nearby gas clouds with such force that they fragmented directly into multiple stellar seeds instead of single stars. Imagine tossing a boulder into a still pond. The ripples force the water into intricate patterns. A supernova's blast wave does the same to star-forming gas, but on an unimaginable scale. In the case of the Octuple system envelorum, astronomers found its stars arranged in an unusually flat plane, a configuration best explained if the cloud that birthed them was violently flattened by a passing shockwave millions of years ago. But supernova don't just shape these systems, they might keep them alive. The same blast that triggers star formation also injects turbulence into the remaining gas, preventing the newborn stars from immediately falling together and merging. Systems like Ty Coronii Australis show this beautifully. Their stars orbit each other at just the right distances to avoid catastrophic collisions, as if some unseen force carefully spaced them apart. That force, likely the fading echo of a supernova's energy, stirring the pot long enough for gravity to work its magic without letting things boil over into chaos. The most dramatic evidence comes from runaway stars within these systems. Some members, like the blue straggler in HD 99999, move at peculiar velocities that suggest they were given a gravitational kick, possibly by the asymmetric explosion of the very supernova that enriched them. It's cosmic irony. The same event that contributed heavy elements might also have altered the system's dynamics, nudging stars into orbits that somehow stabilized rather than destroyed the fragile octuple arrangement. Yet supernova influence isn't always constructive. In the system V833 Centauri, one quadrant is suspiciously empty, a void where at least two stars should exist based on orbital dynamics. The leading theory, a nearby supernova's blast was so powerful it literally stripped stars away, like a cosmic hurricane tearing branches from a tree. The survivors show odd chemical enhancements on just one side of their atmosphere's stellar tan lines, where supernova debris only partially sprayed them during the catastrophe. These layered clues are forcing astronomers to reconsider galactic history. If supernova played a role in forming or reshaping octuple systems, it suggests these stellar families might be more common in regions with violent pasts, near galactic spiral arms or ancient star clusters where massive stars lived fast, died young, and left behind chemically enriched chaos. Every unusual isotopic ratio, every oddly stable orbit in these systems might be a message in a bottle from some long-dead star's final moments. The universe, it seems, builds its most complex stellar families not just through gravity's patient work, but with the hammer blows of stellar catastrophes we're only now learning to read. In the noisy cosmic symphony of octuple star systems, where stellar winds howl and magnetic fields crackle with energy, astronomers have stumbled upon a baffling phenomenon: systems that defy all expectations by remaining eerily quiet. These silent octuplets emit barely a whisper of the radiation their chaotic dynamics should produce, like cosmic stealth fighters hiding in plain sight. The enigma began with System HD 199999, a tightly packed family of 8 stars that should have been a cacophony of X-rays and radio waves based on its configuration. Yet when telescopes tuned in, they detected less activity than our own sedate sun, a paradox that turned stellar physics on its head. The silence isn't just absence, it's an active mystery. These systems contain all the ingredients for cosmic fireworks: massive stars with hurricane-force winds, tight binaries transferring mass at furious rates, and tangled magnetic fields primed for explosive reconnection. Yet somehow, the expected electromagnetic crescendo never materializes. One clue emerged when researchers analyzed the system envelorum silentium, where sophisticated modeling revealed a bizarre self-canceling effect. The stars' overlapping stellar winds collide with such precision that their energies dissipate as subtle heat rather than radiation, like ocean waves perfectly timed to neutralize each other's splash. Even more perplexing are systems where radio silence extends to expected gravitational wave emissions. While most tight stellar binaries generate ripples in spacetime, silent octuplets like TUBE 8802 show gravitational wave outputs 100 times weaker than predicted. The leading theory points to orbital inclinations. These stars might whirl around each other at angles that direct their gravitational ripples away from Earth, like a lighthouse beam sweeping unseen through the cosmic dark. Others suggest exotic physics at play. Perhaps dense plasma clouds between the stars absorb outgoing radiation, or magnetic fields trap charged particles so effectively they can't escape as detectable emissions. The most tantalizing silent systems challenge our understanding of stellar evolution itself. In the case of HIP 77086b, 7 stars blaze with expected intensity while an eighth companion, a massive O-type star, emits less ultraviolet light than a dwarf star a tenth its size. Spectroscopic analysis revealed its outer layers choked with unusually cool, dense gas, as if something had thrown a cosmic blanket over its nuclear furnace. The best explanation: this star might be wrapped in a previously unseen type of megamagnetosphere, its magnetic field so strong it acts like an invisible dam, bottling up radiation that would normally flood into space. What makes these silent octuplets revolutionary isn't just their defiance of expectations, it's what they reveal about the universe's hidden diversity. For every rule astrophysics establishes about stellar behavior, nature seems to have crafted an exception. These quiet rebels force us to question fundamental assumptions. Do we truly understand how stellar winds interact in complex environments? Are there unknown mechanisms for energy dissipation lurking in crowded systems? Each muted system we discover isn't just a curiosity, it's a cosmic clue, hinting at chapters of stellar physics we haven't even begun to read. As telescopes grow more sensitive, the hunt intensifies for other silent operators hiding among the celestial noise. Some might be rare transitional states, caught in brief moments of equilibrium before erupting into expected violence. Others could represent an entirely new class of stellar family, operating by rules we're only beginning to decipher. One thing's certain: in the universe's grand narrative, the quietest characters often have the most surprising stories to tell. At the very edges of what we thought possible for stellar families lies a cosmic behemoth, the largest known octuple system, a sprawling gravitational empire where stars separated by distances vaster than our entire solar system still cling to one another through invisible threads of gravity. Meet V136 Orionis, a stellar collective so expansive that light takes nearly 3 months to travel from one end to the other, yet whose 8 members remain irrevocably tied in a slow-motion ballet across the millennia. This isn't just another multiple star arrangement, it's a challenge to every assumption about how gravitationally bound systems behave at the extreme edges of scale. What makes V136 Orionis so revolutionary is the sheer audacity of its structure. Unlike tightly packed octuplets where stars whirl around each other in frenzied orbits, this system's members are arranged in 2 distinct tiers. 4 stars orbit relatively closely at the core, though close here still means separations wider than Pluto's path around the Sun, while 4 others trace lazy, elliptical orbits so vast they make the Oort cloud look like a stone's throw. The outermost star, designated component H, wanders so far that its gravitational tether to the core group is almost imperceptible, detectable only through painstaking century-long observations revealing its path ever so gradually curving back toward its siblings. The system's discovery came through an unlikely hero: archival data. Astronomers combing through century-old photographic plates noticed that several seemingly unrelated stars in Orion were drifting across the sky in perfect parallel, like ships sailing in formation. Modern Gaia satellite measurements confirmed the unthinkable: these stars shared not just motion but origin, their velocities and chemical compositions betraying a common birthplace despite their ludicrous separation. Tracking their subtle gravitational sway required stitching together observations from 18 different telescopes, creating a multi-wavelength mosaic that revealed the system's hidden architecture. Here's the true marvel: V136 Orionis shouldn't exist. At these distances, galactic tides and passing molecular clouds should have ripped the system apart billions of years ago. Yet somehow, against all odds, it persists. The secret may lie in its unusual birth environment. Spectroscopy shows all 8 stars are metal-poor relics from the early universe, suggesting they formed in an unusually dense, quiet pocket of primordial gas where minimal turbulence allowed their fragile bonds to endure. Their survival hints at a lost era when the Milky Way's gentler conditions permitted such delicate cosmic spiderwebs to form, and against all odds remain intact. Even more perplexing are the system's dynamics. The outer stars don't follow the orderly ellipses of planets. Their paths resemble tangled spaghetti strands, influenced not just by the core group but by each other's intermittent gravitational nudges. Simulations show these stars engage in a bizarre game of cosmic hot potato, transferring energy through rare close encounters that subtly adjust their orbits over eons. One star might dive inward toward the core, only to have another's gravity slingshot it back outward millennia later, creating rhythms that play out over timescales longer than human civilization. This gargantuan system isn't just a curiosity, it's a missing link. Its existence forces us to reconsider where we draw the line between true star systems and mere stellar associations. If stars separated by trillions of kilometers can remain bound, how many other seemingly isolated stars might be part of unrecognized supersystems? Every new observation of V136 Orionis peels back another layer, revealing a universe far more interconnected and far more stubborn in maintaining those connections than we ever dreamed possible. While V136 Orionis sprawls across unthinkable distances, its polar opposite exists in the cosmic record, the smallest known octuple system, a claustrophobic stellar mosh pit where stars orbit so close they nearly graze each other's atmospheres. Meet System X, a gravitational tightrope act where 8 stars cram into a space smaller than Earth's orbit around the Sun, whirling around one another in orbits measured not in years but mere days. This isn't just compact, it's stellar intimacy pushed to the brink of catastrophe, where gravitational forces stretch the very definition of what stars can endure. The system's discovery came via telltale flickers in Kepler Space Telescope data. Light curves so erratic they resembled a malfunction. Instead of the smooth dimming of a transiting planet, the star's brightness plummeted in jagged, unpredictable steps, as if multiple objects were constantly eclipsing one another in a frantic celestial jig. Follow-up spectroscopy revealed the truth. Not 1, not 2, but 8 spectral signatures superimposed, their Doppler shifts betraying orbital velocities topping 500 kilometers per second. Here, stars don't just orbit, they race, completing full revolutions faster than a lunar cycle, their surfaces distorted into teardrop shapes by relentless tidal forces. What makes this system so extreme isn't just proximity, it's the delicate balance preventing total collapse. In most tight binaries, stars either merge or stabilize at safe distances. But System X defies the odds through a phenomenon called hierarchical stability. Its stars are arranged in 4 ultra-close pairs, each locked in a gravitational embrace so tight they behave like single objects to the outer stars. These meta-stars then orbit one another in wider, though still absurdly close configurations, creating layers of gravitational order within the chaos. It's akin to a nested Russian doll where each layer spins at breakneck speeds, yet the whole structure somehow holds together. The physical consequences are staggering. Stellar atmospheres in these tight binaries stream into colossal tidal bridges, transferring mass in continuous loops like water sloshing between connected buckets. In System X's most intimate pair, two stars separated by less than one stellar radius, this exchange happens so violently it generates X-ray flares detectable across the galaxy. Meanwhile, the system's collective light output fluctuates by 20% hourly as stars eclipse, reflect off each other's surfaces, and stretch under gravitational strain. For hypothetical planets here, though none could likely survive, the sky would resemble a strobe-lit disco, with multiple suns rising and setting in chaotic succession, casting ever-shifting shadows. Yet the true marvel is how such systems form at all. Traditional star formation models struggle to explain how a single gas cloud could fragment into 8 distinct cores in such a tiny volume without collapsing into a single massive star. One radical theory suggests System X might be the surviving core of a dense protostellar cluster, where gravitational interactions ejected lighter stars while the most massive members sank to the center, tightening their orbits over eons. Another posits that the system was born as a single massive star that fissioned under rapid rotation, a cosmic mitosis event we've never observed directly. The implications ripple beyond curiosity. Systems like System X serve as natural laboratories for studying stellar evolution under extreme conditions. Their breakneck orbits amplify relativistic effects, allowing astronomers to test Einstein's theories with precision impossible elsewhere. They also preview the universe's far future. When most stars have burned out, tight binaries like these will dominate, their slow in-spirals emitting gravitational waves that may one day be the only celestial churn in an otherwise dark cosmos. For now, they stand as cosmic daredevils, performing gravitational acrobatics where one wrong move could mean stellar annihilation, and rewriting the rules of celestial mechanics with every dizzying revolution. Among the swirling stellar chaos of octuple systems, some astrophysicists are chasing an even wilder possibility. What if certain members aren't stars at all, but unimaginably dense remnants called quark stars or strange stars? These theoretical objects represent matter pushed beyond neutron star limits, where atomic nuclei dissolve into a primordial soup of quarks under pressures so extreme they rewrite the rules of physics. And octuple systems, with their relentless gravitational squeezes and violent collisions, might be the perfect cosmic pressure cookers to forge them. Consider the case of System HD 40591, where one star emits X-rays with a pulse pattern that defies all neutron star models. Its surface temperature suggests an object far denser than physics allows, radiating as if its entire crust were a single quark gluon plasma. The state matter existed in just microseconds after the Big Bang. Then there's the bizarre thermal signature in V1735 Cygni, where a compact object shows heat distribution identical to theoretical quark stars, with a surface so smooth it lacks the mountains and valleys seen on neutron stars. These anomalies have researchers wondering, could octuple systems' extreme environments crush neutron stars into even stranger forms? The physics gets wilder the deeper you dig. Strange stars, hypothetical objects where quarks convert into strange quark matter, would behave unlike anything in our stellar catalogues. Their cores might contain pockets of absolute stability, where matter achieves perfect density and never decays. Some models suggest they could even develop crusts of ultra-dense nuclear pasta, with structures ranging from spaghetti-like strands to lasagna sheets, all while orbiting 7 other stars in gravitational mayhem. Imagine a star-like object where a teaspoon of material weighs as much as Mount Everest, spinning in resonance with stellar siblings that unknowingly dance around a cosmic anomaly. The most tantalizing clue comes from gravitational wave observatories. When neutron stars collide, the resulting vibrations in spacetime encode information about their internal composition. But in octuple systems, certain merger signals show unexpected overtones, frequencies too high to come from conventional neutron stars, yet matching predictions for quark matter's oscillations. It's as if the universe is whispering that under octuple systems' extreme conditions, matter crosses a threshold where protons and neutrons cease to be, leaving only raw quark essence behind. Yet the smoking gun might lie in these systems' magnetic fields. Quark stars are predicted to generate magnetic fields so intense they distort the quantum vacuum itself, creating observable gaps in their emission spectra. Recently, the system TY234599 exhibited this exact signature. One member's magnetic field measurements came back off the charts powerful, with light polarization patterns that conventional magnetars can't produce. If confirmed, it would prove nature has found a way to compress matter beyond neutron degeneracy pressure, creating objects that shouldn't exist except perhaps in the gravitational crucibles of 8-star chaos. The implications ripple far beyond cataloging exotic stars. If quark matter exists in these systems, it could explain long-standing cosmic mysteries like certain ultra-high-energy cosmic rays or even dark matter's nature. Some theories suggest strange stars could act as dark matter factories, their quark reactions producing hypothetical particles that evade detection. Others propose that quark stars' unique neutrino emissions might solve the missing antimatter problem. Each octuple system hiding such an object becomes a natural laboratory for physics we can't replicate on Earth, a place where matter itself gets rewritten by forces beyond imagination. While the evidence remains circumstantial, the hunt intensifies with every new observation. Next-generation telescopes capable of measuring space-time vibrations around compact objects may soon spot the telltale quark star glitch, a sudden change in spin caused by their hypothesized superfluid cores. Until then, these systems tantalize us with possibilities, reminding us that the universe's most extreme families might be hiding its most extraordinary secrets. And somewhere in the chaos of 8 gravitationally entwined stars, matter itself might be breaking its own rules. Deep in the gravitational chaos of octuple star systems, astronomers have stumbled upon stellar phoenixes, stars that cheat death in ways that rewrite our understanding of stellar life cycles. These aren't your average celestial bodies, they're cosmic zombies resurrecting from near-total collapse through violent encounters only possible in the extreme environments of 8-star families. Take the system HD 145678, where a seemingly ordinary red giant suddenly flared back to youth, its outer layers torn away by a close encounter, revealing a reignited core burning with the blue-white intensity of a star 10 times younger. This wasn't just stellar rejuvenation, it was a full-blown cosmic resurrection. The mechanics behind these rebirths are as brutal as they are fascinating. In most of the universe, stars age, predictably expanding into red giants before shedding their outer layers to become white dwarfs. But in octuple systems, gravitational chaos interrupts this process. Picture a star midway through its death throes, its core contracting while its outer atmosphere balloons outward. Now imagine another star whipping past at astronomical speeds, gravitational forces stripping away those puffed-up outer layers like a cosmic scalpel. Suddenly, the exposed core, rich with unburned nuclear fuel, gets a second chance at fusion, reigniting in a spectacular stellar second act. The System V409 Lyrae offers an even stranger scenario. Here, 2 white dwarfs, stellar corpses that should have cooled into oblivion, were caught in a gravitational tango with a massive neighbor. As the giant star's gravity tugged on the pair, it triggered a runaway nuclear reaction on one dwarf's surface, essentially reanimating it into a temporary zombie star that burned for centuries before finally detonating. This wasn't just revival, it was stellar necromancy, where dead stars momentarily returned to life through forces no isolated star could ever experience. Yet the most baffling cases involve partial collisions. In the octuple system TY8023, astronomers witnessed a near miss between a red giant and a main sequence star, an event that should have ripped both apart. Instead, the red giant's core was squeezed by tidal forces like a cosmic stress ball, triggering fresh helium fusion in layers that had gone dormant. The result, a star that suddenly brightened by a factor of 10,000, mimicking a supernova's brilliance without the finality. These kiss and revive encounters create stellar hybrids unlike anything in nature, objects with the surface composition of young stars hiding the traumatized hearts of ancient ones. What makes these resurrected stars scientifically priceless are the clues they offer about stellar interiors. Their violent rebirths expose nuclear burning zones normally hidden deep within, giving astronomers unprecedented views of how elements are forged. The zombie star in system HD 22999, for example, revealed unexpected lithium production in its spectrum, proof that certain nuclear reactions can occur outside traditional models when stars are violently perturbed. Others showcase bizarre isotope ratios that hint at previously unknown fusion pathways, like cosmic Petri dishes where gravity and chaos collaborate to rewrite the periodic table. The implications reach far beyond these systems. If stars can be rebooted through gravitational encounters, it means traditional stellar evolutionary tracks, the orderly charts astronomers have relied on for decades, are incomplete. Entire populations of rejuvenated stars might lurk in other crowded environments like globular clusters, their true ages masked by violent pasts. Even crazier, some of these zombies might temporarily host habitable zones as their reignited cores stabilize, creating ephemeral windows where life could theoretically emerge on orbiting planets, only to vanish when the star's borrowed time runs out. As telescopes probe deeper into these celestial horror stories, each discovery blurs the line between stellar life and death. These zombies aren't mere oddities. They're stress-testing our fundamental assumptions about how stars live, die, and occasionally claw their way back from the cosmic grave through gravitational intervention. Their very existence proves that in the universe's most extreme neighborhoods, death is often just the beginning of a far stranger story. Imagine the Milky Way as a colossal tidal force, its gravitational pull stretching and squeezing everything within its domain, including the delicate dance of octuple star systems. Near the galaxy's bustling center, where stars crowd together like city lights, this tidal influence becomes a make-or-break factor for these intricate stellar families. Galactic tides don't just gently tug, they can warp orbits, amplify instability, and even rip apart systems that venture too close to the gravitational fray. Take the Octuple system IRS-13, nestled just a few light-years from Sagittarius A, our galaxy's supermassive black hole. Here, the Milky Way's tides act like an invisible hand, relentlessly kneading the system's structure. The stars don't just orbit each other, they're also wrestling with the galaxy's bulk, their paths subtly distorted by the competing pull of billions of solar masses. Over millennia, these tidal forces can stretch tight binaries wider or nudge unstable orbits past the breaking point, ejecting stars like celestial shrapnel. In fact, simulations show IRS-13 loses one star every 500,000 years, not through internal chaos, but from the Milky Way's persistent gravitational whispers. What makes this tidal influence so insidious is its selectivity. Unlike the violent collisions near galactic centers, tides work slowly, their effects compounding over eons. A star barely holding onto its octuple family might receive a gravitational kick during its orbit's most vulnerable point, like a child pushed at the peak of a swing. Systems further out experience milder effects, but those daring to orbit near the inner galaxy face a cosmic endurance test. The Octuple system GC1476, for example, clings to stability only because its stars orbit in a precise plane that aligns with the galactic tide, an accidental geometry acting as a survival shield. Yet tides aren't always destructive. In rare cases, they might paradoxically stabilize octuplets. The system HD 204569, positioned in a galactic sweet spot, experiences tides that gently reset eccentric orbits, preventing the close encounters that typically trigger chaos. It's as if the Milky Way itself occasionally plays peacekeeper, its gravitational nudges keeping reckless stars in line. This delicate balance hints at an unseen hierarchy, galactic forces acting as both executioner and architect for the universe's most complex stellar families. The ultimate irony, these tides might explain why octuple systems are rarer near the galaxy's core. Like sandcastles too close to the surf, most get dismantled before we can observe them. Those that survive become cosmic time capsules, their very existence proof that even in the Milky Way's gravitational storm, nature finds a way to carve out pockets of improbable order. Scientists aren't content with the handful of known octuple star systems. They're on a cosmic treasure hunt, deploying cutting-edge technology and clever new techniques to uncover more of these gravitational oddities. The challenge isn't just finding 8 stars together. It's untangling their messy light signatures from thousands of other celestial objects. Traditional planet-hunting telescopes like TESS often miss these complex systems entirely, their algorithms confused by the unpredictable brightness variations of multiple eclipsing stars. That's why astronomers are turning to machine learning, training neural networks on simulated octuple systems until the AI can spot their distinctive fingerprints in decades-old sky survey data. One breakthrough came from combining Gaia's precise positional data with spectroscopy from ground-based telescopes like the Very Large Telescope in Chile. By tracking subtle stellar wobbles across multiple wavelengths, researchers identified 3 new candidate systems in the Carina constellation alone, each showing the telltale gravitational tugs of hidden companions. But the real game-changer will be NASA's upcoming Nancy Grace Roman Space Telescope, equipped with a coronagraph powerful enough to block out individual stars in tight groups, potentially revealing fainter siblings hiding in their glare. Radio astronomy is entering the hunt too. The ALMA array recently detected strange millimeter-wave emissions from a system previously thought to contain only 5 stars until the signals revealed 3 more cool, dim members obscured by dust. Meanwhile, teams are revisiting old pulsar timing data, searching for the distinctive gravitational distortions caused when these precise cosmic clocks orbit amidst multiple unseen stars. It's like listening for faint echoes in a crowded room. Each subtle variation in pulse timing could betray another hidden dancer in these celestial ballets. The most tantalizing prospects lie beyond our galaxy, with JWST infrared eyes peeling back dust clouds in the Andromeda Galaxy. Astronomers have spotted several 8-star candidates based on their unusual heat signatures. These extragalactic systems could reveal whether octuplets form differently in varied galactic environments, or if the same gravitational rules apply universally. Every new discovery doesn't just add to the count, it refines our search strategies. Systems found so far suggest octuplets favor certain stellar nurseries like the Orion Complex, where dense gas clouds might foster their formation. Others appear linked to past supernova explosions, their shockwaves potentially triggering multiple star births. As the catalog grows, patterns emerge, perhaps proving these aren't random cosmic flukes, but natural outcomes of universal physics under the right conditions. The next decade promises an avalanche of discoveries as 30-meter-class telescopes come online, their resolution sharp enough to separate tight binaries at unprecedented distances. Combined with gravitational wave detectors tracking subtle spacetime ripples from these systems, we might soon confirm hundreds more, each one a new chapter in the ongoing story of how stars form, survive, and dance together in the universe's most crowded neighborhoods. Somewhere in the distant future, when the universe has cooled to a whisper and galaxies have faded like dying embers, the last octuple star systems will face their ultimate reckoning. These gravitational mavericks, having defied the odds for billions of years, won't go quietly into the cosmic night. Their endings will be as spectacular as their lives, each fate as unique as the chaotic dance that shaped them. Picture the slow unraveling of a system like New Scorpii, over eons, gravitational wave radiation. The faint ripples in spacetime caused by orbiting masses will sap energy from its tightest binaries. Stars that once whirled around each other in days will spiral closer, their orbits tightening like a coiled spring until catastrophe strikes. In the final moments, two stellar giants might collide head-on, triggering a hypernova explosion so violent it outshines entire galaxies. The resulting black hole, fresh from this stellar demolition derby, could become the anchor for whatever stars remain, beginning a new chapter as the gravitational puppet master of a reduced but still complex system. Other octuplets might meet a stranger fate. Consider a system like HD 1, 2, 3, 4, 5, 6, where hierarchical orbits have kept chaos at bay. Here, the outer stars could gradually drift apart, their bonds stretched thin by galactic tides until they become solitary wanderers. Yet the core, a tight quartet of stars, might continue dancing long after their siblings have left, eventually merging into a single, monstrous star. This Franken star, bloated with stolen mass, could live an unnaturally long life before collapsing into a black hole so massive it defies conventional stellar evolution models. Then there's the possibility of a chain reaction collapse. In systems where multiple stars orbit perilously close, the death of one could trigger a deadly domino effect. Imagine a white dwarf, the dense corpse of a dead star receiving one last gravitational nudge from a passing sibling, pushing it over the edge into a Type Ia supernova. The blast could vaporize nearby stars or hurl survivors into the void at breakneck speeds, transforming an orderly octuple into a cosmic crime scene of runaway stars and glowing debris. But perhaps the most poetic fate belongs to those rare systems that form stable hierarchies. These celestial elders might avoid violent ends entirely, their stars gradually cooling into white dwarfs in peaceful succession. Over trillions of years, long after the last regular stars have flickered out, these faint embers could continue their slow waltz, their orbits preserved by the perfect balance struck eons earlier. Some might even become fossil systems, their dim glow the only testament to an era when the universe was young, chaotic, and alive with stellar possibilities. The universe doesn't give out participation trophies, only survivors and casualties in the endless game of gravity. Whether through fire or ice, expansion or implosion, the stories of these 8-star wonders will end as they lived, rewriting the rules, bending physics, and leaving behind relics so bizarre they'll puzzle astronomers in cosmic epochs we can scarcely imagine. From the gravitational mayhem of 8 stars whirling in cosmic chaos to the quiet, impossible longevity of systems older than our galaxy, octuple star systems have shattered every assumption we held about how stellar families behave. These celestial oddities shouldn't exist, not by our models, not by our math, and certainly not by our imagination. Yet here they are, rewriting the rules of astrophysics with every discovery. They've shown us stars that cheat death, black holes hiding in plain sight, and planetary orbits so unstable they make roller coasters seem tame. They've revealed chemical anomalies that defy stellar evolution, gravitational resonances precise enough to rival atomic clocks, and dark matter's subtle fingerprints on orbits we once thought we understood. Consider the sheer audacity of what we've uncovered. Vampire stars stealing life from their siblings, zombie stars resurrected by gravitational encounters, and hypervelocity runaways flung across the galaxy like cosmic cannonballs. We've witnessed stellar collisions forging elements in ways no supernova could replicate, and radio whispers so bizarre they hint at physics we haven't even named yet. These systems aren't just challenging textbooks, they're burning them down and writing new ones in the ashes. And yet, for all we've learned, the biggest revelations might still be ahead. Why do some octuplets thrive while others self-destruct? How many more are hiding in plain sight, their complexity masked by distance or dust? Could planets really survive in such chaos? And if so, what would life look like under 8 suns? The universe has handed us these stellar puzzles not to frustrate us, but to remind us how much wilder reality is than anything we could invent. So as we close this cosmic journey, I'll leave you with this. Look up at the night sky and remember, somewhere out there, an 8-star family is dancing in defiance of every law we thought governed them. And that's the real magic of astronomy. Every answer we uncover births 10 new questions, and the universe always keeps one more secret in its pocket. What's your favorite octuple system mystery? Drop your thoughts below, because the greatest discoveries often start with someone daring to wonder, what if? End of